So we're going to talk a little tonight about the nature of time. We're going to explore a little bit about both space and hyperspaces, whatever those are. And we'll talk a little bit further about this linear assumptions in a manifestly nonlinear world. Now, so let's start with the nature of time. And we're going to get some insights from modern physics here. Time, it turns out, is a physical property. And that is not as obvious as it first may sound, but it is profoundly important to understand, because unless you understand that, you will not fully appreciate much of the biblical text. We know today that we don't live in 3 dimensions, we live in 4. That's why physicists will always use the term space-time. And we'll touch upon Paul's revelation in Ephesians chapter 3. Paul highlights something that many people miss that is of profound significance to all of us. We'll touch on that, and we'll explore a little some lessons from geometry. But it'll be a geometry that goes beyond the Euclidean geometry that you learned in school. So we'll touch a little bit about that. We're going to talk a little bit about the geometry of eternity. Sounds like a strange phrase, doesn't it? Is time linear and absolute? Most people presume it is. And yet we know today, in the laboratories, if you will, that it is no longer linear and it's no longer absolute. And that changes everything. What we thought was a ruler turns out to be a rubber band. It shrinks and extends depending on circumstances. And many assumptions that we make in our everyday life now prove to be obsolete due to recent scientific discoveries. So this is part of what we're going to be dealing with. So the nature of time, that's our subject for tonight. And I want to start by reviewing some things that you learned in school in the field of trigonometry, the study of triangles. And we learned in school that if you have a triangle, almost any triangle, the angles of a triangle always add up to 180 degrees, right? How many learned that in school? Okay, good for you. And it doesn't matter what kind of a triangle you have. Any triangle, it turns out, apparently fulfills that rule. But suppose now Gary and I go out into a field, a large field, and we lay out a triangle, and we discover the angles of that triangle that we laid out on this large field adds up to more than 180 degrees. What would you conclude? Some of you would say, well, that's what I expect from Chuck and Gary going on an assignment like that, you know. No, so you recheck our work and you discover, much to your amazement, that it's more than 180 degrees. And what we've discovered then is that those rules we learned are only true for a universe of 2 dimensions. That's why it's called plane trigonometry or plane geometry, because it's true in a flat surface, okay? Now, it turns out that if you start studying the globe and you start studying navigation, you quickly discover that you have triangles all the time of more than 180 degrees. You can have a triangle on the planet Earth that has 90 degrees in each corner. Okay? That's more than 180 degrees, by the way. You can add it up and try it out. Okay. It turns out that if you have angles of more than 180 degrees, what you discover is that you are on a convex surface, not flat anymore. If you ever encounter a triangle that has less than 180 degrees, then that means you've got a convex surface rather than a concave surface rather than a convex surface. And a hyperbolic paraboloid being a common example of that. But I don't think any of you are worried about encountering one of those. The real point is the realization that a violation of that little rule of 180 degrees is what led Dr. Einstein to realize, as he was grappling with the properties of space, he began to realize that space has more than 3 dimensions. And that's what led to the theory of relativity, because he realized that Planck's constant was a 4-dimensional constant, not 3. And so that's how he led to what we call Einstein's revolution. His special theory of relativity in 1905, where length, mass, and velocity were relative to velocity, was part of it, but then it gets generalized by 1915 at what his general theory of relativity. When we speak of Einstein's theory of relativity, you usually mean his general theory of relativity, in which there's no distinction between time and space. we encounter three spatial dimensions: length, width, and height, and time. A point in this space has existence not only in terms of those three spaces, but in a moment of time. Time is an intrinsic property of the environment that we're in. There's no distinction between time and space. In fact, we now know that we live in a four-dimensional continuum. And this has been confirmed at least more than 14 ways to over 19 decimals accuracy. So it's no longer really a theory. There are aspects and implications that are still quite theoretical. But the point is, this is now a recognized, highly confirmed thing here. So I want to talk a little bit about the dilation of time. There are atomic clocks that are located at the National Institute of Standards and Technology in Boulder, Colorado, and also at the Royal Observatory in Greenwich, England. These are very complex devices, and they are very, very accurate. They're accurate to better than 1 second per million years. And I remember vividly, I was on the board of directors of a company that was acquiring another company, Frequency Time Systems in Boston. We were acquiring this company, and the company we were acquiring, the president was giving us a proud demonstration of their product, which was cesium clocks, basically, and that they're accurate to better than 1 second per million years. And I raised my hand as an acquiring director. I says, I have only two questions. How do you know? And who cares? Well, the way we know is it is from the natural resonance of the cesium atom, which is what gives it this incredible accuracy. And who cares? It turns out that the accuracy of measuring time determines the precision of your navigation. And it's the accuracy of those clocks is what makes your GPS operate. Even when I travel, it mystifies me that I can have a little thing that might put my phone on the rental car and tell it where I'm going and where I want, and it'll tell me which lane to travel in. And it'll tell me that I'm not in the right lane to make a right exit. I mean, the precision of that thing, knowing exactly where I am, whether I'm in the United States or in New Zealand, driving on the left side, doesn't matter. It knows exactly. I'll never forget the first time. I happened to be, many years ago, I was renting a Hertz car that had a Magellan, they call it. It was one of the early GPS systems. And I happened to be talking to my wife on the phone. And this woman's voice tells me, be sure to get in the right lane for the coming exit. And Nan pretended not to believe me. I tried to explain that's just this Hertz thing. And of course, she knew what it was, but she wouldn't let go. She just kept, who's that in the car with you, you know? But anyway, so in today's world, we're beginning to take so many of these things so for granted. And yet part of this is because of the precision at measuring time. But let me tell you something about these two clocks. There's these elaborate, highly precise devices, one in Boulder, Colorado, and one in Greenwich, England. They're accurate to 1 second per million years. And yet every year, there's 5 millionths of a second off. They don't stay in step. So the question you want to ask, okay, which of these is the accurate one? Okay? It's the one in Boulder that's 5 seconds per year faster than the identical clock in Greenwich. Which one's correct? They're both correct. Time itself is different there than here. Why? Because Boulder, Colorado is at 5,400 feet altitude. It's in the Denver area, that's high altitude. The one in Greenwich, England is 80 feet above sea level. So one is higher than the other. If I had such a clock here on the platform and raised it 1 meter, okay, it speeds up by 1 part in 10 with 16 zeros after it. Not very much, but it's predictable and measurable. Time changes with gravity. That's the difference here in gravity. So these atomic clocks are faster by 1 part in 10 with 16 zeros after it for every meter in elevation. So see, a time measurement in a weaker gravitational field runs faster than one in a stronger field. So if you're starting to talk about days or years or months, you really have to say, in what gravity field are you talking? Because they're different, by the way. Near the surface of the Earth, there's this 1 part in 10 to the 16th per meter, and for whatever it's worth. Now, they actually took some very accurate measurements in aircraft in 1971. J.C. Haley and Richard Keating put 4 cesium clocks around the world. One went eastward and one went westward. And by the time you account for rotation and all that stuff, it turns out that the one that went eastward around the world lost 0.059 microseconds, while the one that went westward gained 0.273. Exactly what, when you take all the physics factors, exactly what Einstein's theory predicted. Really astonishing. But the one that's perhaps more graphic and relevant, if you pick up a textbook, almost any textbook in physics that deals with this, they typically will talk about 2 hypothetical astronauts. And we're going to send them to the nearest star, one of them. We're going to leave one of them right here with us, and we're going to send one to the nearest star, which happens to be Alpha Centauri. That's the one that's closest to us. If you go to the night sky, there is a star up there, the closest one to us, that happens to be called Alpha Centauri. We're going to pick that, and in our imagination, we're going to send one of these 2 astronauts. They were both born at the twins, both born at the same instant. And we're going to send one to that star and back, okay? Now, the Alpha Centauri the Alpha Centauri is about 4.5 light years away. A light year is a distance, a very large distance. It's how far light can travel within a year. Light goes pretty fast, and a year is a long time. It's 4.5 of those. That's how far away Alpha Centauri is. So we're going to send this astronaut we're going to imagine that we could send him at half the speed of light. So he's going to go 4.5 light years away at half the speed of light. It's going to take him 9 years to get there, right? 9 years back. Okay. So that's on the Earth. Here on the Earth, he will leave. Take him 9 years to get there and 9 years back. On our logbook, he will have been gone 18 years. You with me so far? Okay. Now, that's on the Earth. Let's take a look at his logbook, so to speak. He's traveling in the spaceship. And it turns out there's a Lorentz transform. There's a mathematical formula that works this out for us. But it turns out that his clock, well, he'll come back from this trip, and when he gets back, he will be 2 years and 5 months younger than his twin brother. And if that doesn't bother you, you weren't listening carefully, okay? In other words, his time is different than our time here on the Earth. Why? For a lot of different reasons, partly because he went near the speed of light and coming back. You with me? To dramatize this just a little bit further, let's imagine that we could have sent him at almost the speed of light, 99.99% speed of light. Okay, so then his round trip would only take 9 years. He's going twice as fast, right? Okay, so it's 9 years. Except when he gets back, he will have noticed only 33 days. So when he gets back, he says, I sure wish I would have bought some of that Microsoft stock before I left, you see. Or Apple, or take your pick. Okay. So the point is, his time and our time is noticeably different. And the issue here isn't this issue of space travel and stuff. The issue is to understand that time is physical. It changes with mass, acceleration, or gravity, among other things. So it's a physical property. Okay? It's not uniform. It's a physical property. And it varies with mass, acceleration, gravity, among other things. If you get into the mathematics of this, you quickly discover there's a whole bunch of parameters that have to be defined to get equivalence here. Okay. Now, what this also means, by the way, is that you and I live in more than 3 dimensions. Yeah, we have a length, width, and space, spatial dimensions. We also have time that is measurable and physical. Ooh. Okay. How many dimensions do we live in? It turns out 10 is a current estimate. More than 3 is the main point. Okay. Let's talk a little bit about the nature of God. Is God subject to the restrictions of mass? I don't think so. Does God accelerate or deaccelerate it? I don't think so. Is God subject to gravity? I don't think so. So is God subject to time? No, of course not. See, God is not somebody with lots of time. That's our concept of eternity, having a lot of time. No, 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 no. God is outside the dimensionality of time altogether. He's outside those restrictions. And that uniqueness is his alone. That's probably not true of the angels either, by the way. God alone it's his personal imprint. And he takes advantage of that to authenticate his message. See, that's what Isaiah means when he says, "Thus saith the high and lofty one that inhabiteth eternity." What does he mean by that? That he has lots of time? No. He's outside this realm of time itself. And that has implications for all of us. If God has the technology to create us, does he have the technology to get a message to us? Of course. He can create us. He certainly get a message to us. The problem is, how does he let us know the message is really from him? Let me give you an example. Let's assume you're an undercover agent in a foreign country. And you get messages from your superior, from control or your capital, whatever. Except the host country has discovered that there may be they've found a way to create synthetic messages. You're in your hotel room, and you've got these 10 messages that have somehow arrived to you. How do you tell which one's authentic? How do you know which one of these messages spread out on your bed here really came from headquarters and wasn't synthesized by the enemy? How do you tell? There has to be something about them that only you and your headquarters know. Some use of words, some clever trick. There's some method of authentication so that you know, aha, that's the one that's real, the rest of these are phony. You follow me? That's what we mean by authentication. Well, how does God authenticate this? We have this collection of books in our laps called the Bible. How do we know it's from him? How many believe the Word of God is the Word of God? Why? Why do you believe that? Well, somebody told me. Or it says so. No. How do you know it's really from him? How do you know it's not just a very ingenious collection of fables and something? How do you know it really came from God? Well, how does he authenticate his message so we know it's really from him and not some kind of contrivance or a fraud or a collection of coincidences or something? Well, he declares the end from the beginning, and from ancient times, things that are not yet done. He demonstrates his ability to be outside time. How does he do that? By telling us what happens before it happens. And I don't mean in a few hours, centuries in advance. He gives the exact day that certain things are going to happen. And he describes circumstances that are impossible and crazy, and yet they happen. Exactly like he said. And the more you see that, the more you embrace that, suddenly you begin to realize you're dealing in a communication with somebody that's extraterrestrial, outside our time domain. And that's so fundamental. We also have another problem. We think of time as linear. But when we were in school, the teacher went to the blackboard and drew a line from left to right. And the left end was the beginning of something, the birth of a famous person or the founding of an empire, what have you. The right end was the end of that. There's a beginning and end. How many have made timelines in school? How many of you went to school? I'm kidding. All right. So what we do because of that background, when somebody uses the word eternity, we tend to imagine what that means. It's like a line that starts at infinity over here on the left and goes to infinity over here on the right. We think of eternity as having lots of time. That makes good poetry, but it happens to be very bad physics. Because eternity is not having lots of time, it's being outside the dimension of time altogether. Let me take this line that I've used and pretend it comes out from the screen towards you. Can I represent that sort of with this curve? Just imagine it's coming out at you. You and I are at a point in that time called the present. Okay? Behind us is the past. And the front of us is the future. Okay? The past is a memory. The future is a hope. We're between those two. That's why we call it a present. It's a gift. It's a gift. See a little pun there? I went by you there. Sorry. Okay. Now, see, for us, what's past is behind us. What's forthcoming is coming, and we don't know what's coming. But if I'm outside that line altogether in eternity, it's conceivable for me to be able to see all three at the same moment, so to speak. God is outside the dimension of time. He can see the past, obviously, and the present, but he also can see the future as clearly as he saw the past. Now that leads to another interesting conjecture I'll just leave with you to think about, is those arrows can go the other way. Somebody that died 1,000 years ago, and someone that died yesterday, and someone that gets raptured 3 months from now, may all arrive at his throne at the same moment. Ooh. That should alter your three-dimensional, four-dimensional perceptions here. But let's move on here. I love one of my favorite quotes of Dr. Einstein is that he says, people like us who believe in physics know that the distinction between the past, the present, and the future is only a stubbornly persistent illusion. Because he really had a grasp of time far beyond most philosophers, of course. Now, you and I are sitting here with in our lap a collection of books. We call it the Bible. We use it singularly, but it actually is a collection of 66 books. And if you're not confused yet, I'll point out to you it's actually 70, not 66. But if I said that on the radio, it would confuse all my listeners. Because the book of Psalms is 5 books. And if you break that down, you really have 70 books. But if you start that discussion, you get everybody confused. Okay. No, we'll stick with 66 books. That works for our purposes. And they were written of a period of almost 2,000 years, by our reckoning. Now, the interesting thing is, as we discover that it was penned by over 40 different guys. Some say 44. There's a few that there's some ambiguity about because they're really edited and pulled together. The point is, there are more than 40 authors that pulled these together over 2,000 years. And one of the incredible discoveries in my life, since my specialty from the beginning was in the information sciences. And as you study information sciences, you get, that's a field that is perhaps a little specialized. But from that perspective, I encountered 2 discoveries that changed my life. The first discovery was that these 66 books, even though they're penned by over 40 guys over almost 2,000 years, they're an integrated message system. Now, what do I mean by that? I don't mean that there's a theme in the old that's fulfilled in the new and all that. No. Far more than that. These 66 separate books, penned by over 40 different individuals who didn't even, for a large part, didn't even know each other, because they were spread over 1,700 years. But in this package of writings, we discover that every detail is anticipated by a deliberate, skillful design. The very words, the very letters, the use of idioms, the very structure of the text demonstrates an integrity of design that went far beyond the horizons of any one of the writers. Now, when you grapple with that, you first of all really, don't take my word for it. You have to discover this on your own. But as you do, as you begin to uncover examples of this, what you begin to realize is that the origin of that collection had to come from outside time itself. It wasn't dreamed up by Moses, by great insights. It wasn't these prophets didn't somehow accidentally lay out these genealogical and other details. No. There's an architect organizing this from outside time. And that's demonstrable by just studying the text. I get so tired when I hear one of these well-meaning Christian kind of guys on the television say, well, you can't prove the Bible, but. They ought to make some very positive point, but they seem to have to preference it with this presumption, well, you can't prove the Bible. That just shows their own lack of information. They're uninformed. Yes, you can prove the Bible by simply this, by discovering the integration of that design, and that's just a question of doing some homework, and then try to explain the origin of that design any other way than having come from outside time. Yes, you can prove the Bible. And the fingerprints of the author are all over the creation and all over the Bible, and they are in concert. So we're going to explore a little bit as we go on here about the boundaries of our reality, because the message we're dealing with is from outside our reality. And I'm going to use Da Vinci's Vitruvian Man a representation of our anthropic reach. We as men, how far can we reach? I'm just going to represent that by the middle here. We are man. We're in the middle of this, okay? And we're going to talk more about the discovery by scientists that we seem to be dimensionally in the very center of the universe. From the very largest, very smallest, we're right in the middle somehow. And I'll come to that later. But there we are. We're going to explore tonight a little bit about largeness. I'm going to take size as a horizontal ordinate here, okay? So things to the right are big, things to the left are small, bigger or smaller than man. So we're going to go tonight, we're going to go to the right. We're going to go to bigness, largeness, if I can call it that. And the ultimate largeness would be the study of astronomy, astrophysics, the heavens, the universe. That's focusing our attention to bigness, if you will, okay? So the shocking discovery of 20th century science was the discovery and the realization that our universe is not infinite. It is finite. And if you haven't studied that or you don't realize that, that comes as a huge shock to any thinking person. Because we've all sort of grown up thinking that the heavens go on forever. We discover, no, they don't. They might be expanding, but they're finite. And that's demonstrable. It's now understood and accepted. Most of these concepts get beat around for a generation or two or three. But this is one that's been nailed. It's finite. And I want to explore that a little bit. We know from the thermodynamics that there's a thing called thermal decay. You know, hot flows from hot to cold. You ever notice that? Anyone want to debate that? We all have experienced that heat flows to cold, right? Heat is something, cold is the absence of that, so the heat flows to where there isn't any, right? Okay. Now, if the universe was infinitely old, the temperature throughout the universe would be uniform, because heat is flowing from hot to cold. So if it was infinitely old, that would have all happened. In other words, the realization in thermodynamics is that age is a function of that disparity. Okay? Now, since the universe is not uniform, that means it's not infinitely old. That means it had a beginning. Wow, big deal. Science is still trying to wrestle with that reality. They obviously know it had a beginning. And the way they explain it is first there was nothing, and then it exploded. And if you think that makes logical sense, you're in the wrong class. Okay. No, the universe had a beginning, and attempts to explain that fall under a category of theories called the Big Bang. And there's 4 or 5 basic ones, and none of them work, by the way. That's part of that's why it's such a hot topic in physics or astrophysics, is because each presumption you make turns out to be refutable. Well, it oscillated. Well, then there's a loss. There's a entropy loss issue, and you go on and on. So the problem is they can talk about what they think happened in the first few seconds or whatever. They can't explain how did it happen. What started it? There had to be something making it happen. Really? Okay. That also means it's destined for an ending. If heat is flowing from hot to cold, and eventually that all happens, and there is no more difference in temperature, there is no more possibility of doing work in the universe. All work is a function of temperature differences, in effect, energy differences. And so we know it had a beginning, and the shock is we know that someday, billions and billions and billions of years from now, or whenever, it's going to have an ending. Okay? Now this is the reality we need to face. The Big Bang is what we call the beginning of it, and the heat death, the ultimate heat death, is what scientists call the end of this. And the point is that it's finite, had a beginning and an ending. That's a disturbing thing to come to grips with. We're in a temporary environment. Wow. That's especially disturbing when you discover that you are not temporary. This part of you that has no mass, call it soul, spirit, call it what you will, it's massless, so it has no time, so you're eternal, but you're in a temporary environment. Wow! Does that give us some insights biblically, if you will? Now, you talk about black holes. In the idioms of relativity, gravity distorts space-time. And as gravity is stronger in the immediate vicinity of denser objects, so space-time is increasingly distorted as an object with particular density shrinks. That's changing time. Try to get used to that idea. At a crucial size, known as the Schwarzschild radius, space-time bends completely around itself, cutting off the region of space-time inside the hole from the rest of the universe. They call that a black hole, okay? Objects can fall into the black hole, but within a sphere called the Schwarzschild radius, nothing, not even light, can escape. That's why they call it a black hole. This is a twisting or a distortion, if you will, of space-time. And it's obviously a subject of a lot of theoretical discussions, and they do know of some of these that are identifiable in the universe. And now, surprisingly, about this, there are some solutions to Einstein's equations of general relativity that appear to represent models that could permit loops in time. That may shock you, and it's argued about among the physicists. But it's a concept I just want you to know exists. There's an area of the Schwarzschild surface of the hole that is a measure of its entropy, or randomness, if you will. And if it should shrink, entropy would decrease, implying a reversal of time. I'm just trying to stretch I'm not trying to get to a point here, other than just to stretch your understanding here a little bit. Can time go backwards? Maybe, we're not sure. In quantum physics, that's a topic for a future session, but in quantum physics, that study of tiny, tiny things, subatomic particles, two representations of particle collisions in the Feynman diagram are identical. The Feynman diagram I'll show you here in a minute. An electron and a positron appear when they see in a cloud chamber or whatever. They seem to annihilate each other. But that same event can be represented as the electron in a time reversal. Let me show you what I mean. A Feynman diagram is where you plot space against time, and you have an electron, a gamma ray, and it breaks off to an electron and a positron, which when it collides with an electron annihilates itself. That's the way it's usually explained. Okay? Now, except the same thing can be represented another way. And that is that electron on the left is in a time reversal. A positron is an electron in a time reversal, is another way of looking at it. See, the real issue here is do we have a positron, or is that positron an electron in a time reversal? And a particle physicist will tell you those are both equivalent. Is it possible that electron went backwards in time? Possibly. We'll see. Now, there are all kinds of paradoxes of time reversals in literature. And there are events having no beginning and time warps. There's also a lot of literature about trying to alter previously recorded events. You have that shows up in literature all over. The Time Machine being one of the classic examples. Somewhere in Time, a movie that was popular for a while. Back to the Future was a popularization of that idea. The Terminator series dealt with this whole idea of time warps and so forth. And I couldn't resist the temptation of showing you what has to be the most absurd example of time warps. We've all encountered some of these in literature, and we find them entertaining. We all realize they're not real, they're just entertainment. And Robert Heinlein, who's probably one of the most famous of the science fiction writers, has contributed what has to be the most absurd extreme of this, his classic. And basically, he talks about his imaginary story. A baby girl is mysteriously dropped off at an orphanage in Cleveland in 1945. So far, so good, huh? Jane grows up lonely and dejected, not knowing who her parents are, until one day in 1963, she is strangely attracted to a drifter. She falls in love with him, but just when things are finally looking up for Jane, a series of disasters strike. First, she becomes pregnant by the drifter, who then disappears. Second, her highly complicated delivery, doctors find that she has both sets of sex organs, so to save her life, they're forced to surgically convert her to a him. Finally, a mysterious stranger kidnaps her baby from the delivery room. Reeling from these disasters and rejected by society, scorned by fate, he becomes a drunkard and a drifter. Not only has Jane lost her parents and her lover, he has lost his only child as well. Years later, in 1970, he stumbles into a lonely bar called Pop's Place and spills out his pathetic story to an elderly bartender. The sympathetic bartender offers the drifter a chance to avenge the stranger who left her pregnant and abandoned on the condition that he joined the Time Travelers Corps. Both of them enter a time machine, and the bartender drops off the drifter in 1963. The drifter is strangely attracted to a young orphan woman who subsequently becomes pregnant. And the bartender then goes forward 9 months, kidnaps the baby girl from the hospital, drops off the baby in an orphanage back in 1945. Then the bartender drops off the thoroughly confused drifter in 1985 to enlist in the Time Travelers Corps. Now the question of, the drifter eventually gets his life together, becomes a respected and elderly member of the Time Travelers Corps, then disguises himself as a bartender and has his most difficult mission, a date with destiny, meeting a certain drifter at Pop's Place in 1970. Question: who is Jane's mother, her father, grandfather, grandmother, son, daughter, granddaughter, and grandson? They're all the same person. Now, this has to be the most convoluted conception. The girl, the drifter, the bartender, of course, are all the same person. And the paradoxes here are manifold in terms of the twisted genealogy. She's her own mother and father and so forth. She's an entire family tree in herself. So Robert Heinlein, whatever, it's a silly story, of course, but he's probably woven. I cannot imagine anything getting sillier or more complex. Okay. I'm reminded, people like us who believe in physics know the distinction between the past, present, and future is only a stubbornly persistent illusion. I think that's Robert Heinlein's challenge to that, I suspect. But anyways, enough of this foolishness. Let's move on. Linear time. We tend to presume that time is linear. We talked about beginning and end and so forth. So we, in time, move forward, don't we? And we can look back. We can't move back, except in the fiction foolishness of these science fiction things. We can't move back, but can we look forward? Not really. We pretend to, we think to, and there are mystics that try to, but the only one that knows the future is God. Satan and his minions may try to simulate that in various clever ways, but that we can move forward, look back. We can't move back, and we are not very good at looking forward. And so, can time really go backward? If it could go backward, how could you tell? Suppose at midnight tonight, time started to go backwards. So would all clocks, so would all time. Turns out, it's a non-trivial thing. If you were suddenly disturbed, if somehow through one of my talks, and you suddenly became concerned, gee, maybe, am I in a time reversal? How would you tell? You can't tell by looking at a clock. How can you tell if time's going backwards? There is a very simple way to tell. What you do is you get a deck of cards, and you shuffle them. And as you shuffle them, they get more ordered. You're going backwards. See, time moves towards randomness. Time goes from order to chaos, always. You ever notice that in your locker in school? Or the garage, you spend a Saturday and get it all organized for how long? Huh? The closet, in the front hall closet, whatever. It goes from order to chaos. That's just life. That's true in every field of science. It's called the entropy laws. They have thermodynamic rules. So if you saw a reversal of entropy, you're going backwards in time. One way you do that would be shuffle cards, and if you did it and they came out in bridge order, you'd be very uncomfortable, wouldn't you? Okay. So the entropy, shuffling a deck of cards. Randomness toward order would be a reversal of entropy and hence time. Okay. Okay, well, we've talked a little bit about the nature of time. I'm going to change slightly, and we're going to talk about the nature of space and hyperspaces a bit. We find the term throughout the Bible, stretching the heavens. I want to talk a little bit about the fabric of space as we think of it. Is this just a metaphor? I saw the heavens stretched out. Is that just a poetic metaphor? Job says, who alone stretches out the heavens? In Psalm 104, stretching out heaven like a tent curtain. Isaiah 40, who stretches out the heavens like a curtain and spreads them out like a tent to dwell in. Jeremiah says he has stretched out the heavens. The Lord who stretches out the heavens, Zechariah also picks up, and so forth. I could go on and on like this in dozens of passages where consistently the Bible talks about the heavens as being stretched. In fact, it gets worse than that. We know that space today, you and I think of space as an empty vacuum. You know, we visualize someone in a spacecraft out there having to get out in a spacesuit for obvious reasons, and yet we presume that the vacuum is empty. It's not empty. That may come as a surprise to you. Isaiah tells us it can be torn. Isaiah 64, the space can be torn. It can be worn out like a garment, really. Psalm 102. Hebrews, Haggai, and Isaiah all speaks of the heavens being shaken. If it's empty, how can you shake it? 2 Peter talks about it being burnt up. Revelation talks about it being split apart like a scroll. Rolled up like a mantle in Hebrews 1 and a scroll by Isaiah 34. Now that's a whole big thing. If the heavens can be rolled up, in order for something to be rolled up, it must be in some sense thin. And it must have an additional dimension to roll it up. You can take a two-dimensional photograph, and to roll it up takes a third dimension, doesn't it? You see the idea of being rolled up or being scrolled is an additional dimension. So there's some dimensions at which must be thin. It can be bent. So there must be some direction it can be bent toward. So that all implies from this text that there are additional spatial dimensions. Space is three-dimensional. There must be four for any of these things to happen. An additional dimension, right? So the properties of space, you may think it's empty. It may shock you to discover that the physicists will speak of zero-point energy. The smallest point in space has 10 to the 95th, with 95 zeros after it, ergs per cubic centimeter. That's the most intense energy field you can imagine. Permittivity. It has an absolute dielectric constant. It has permeability. That's a magnetic constant. If you're a radio ham or in electrical engineering, you know that space has an intrinsic impedance. That's why you have antennas, to try to match the impedance of space. It has electrical properties. It's not empty. It has electrical properties. The velocity of light is also associated with all of this, and currently they're trying to study the speed of gravity. There's experiments trying to chase that down. Now the other thing is light may not be linear. See, the key properties of vacuum, of free space, include permittivity, permeability, all these things I just mentioned. If any of these change isotropically, then both the atomic behavior and the speed of light could vary throughout the universe. The speed of light may not be constant throughout the universe. We're going to talk more about this in a more advanced session forthcoming. But Dr. Barry Setterfield, his controversial observations about he was the first to recognize the velocity of light is not a constant. And over 20 years ago, when I first got to know the guy and I started mentioning this in some of our studies, I was visited by Hugh Ross and some of my other physics friends who very gently tried to help me, counsel me, so I wouldn't get caught with these heresies saying that the speed of light's not a constant. And I look back at those days very graciously because they meant well, trying to keep me out of trouble. But I chose to stay with Barry, and it turned out he's now been confirmed. They now know the speed of light is not constant. In fact, there's a lot of recent papers that explore implications of that. But what's disturbing, he identified this more than 20 years ago, and they don't give him credit for that. The field of physics is just as... anyway, we go on. Setterfield, he analyzed 164 measurements of speed of light, commonly called C, the speed of light, velocity of light, gathered over the last 320 years, which reveal a statistically significant decay of speed of light. And when coupled with the associated C-dependent constants, that includes some 639 values measured by 25 different methods. It still didn't cause these people to pick up on it. A comparison of dates in orbital time from history, archaeologically, corals, tree rings, whatever, with atomic dates from a variety of radioactive isotopes, has provided some over 1,228 data points over almost 5,000 years. And this is all exploited in our briefing on Genesis, the Big Bang, and other things here. William Tift is an astronomer with the University of Arizona. And he's been collecting data for about 20 years on what are called red shifts. Some of you may realize that the stars, if you take a spectrum of it, they have a spectrograph, the stars seem to be shifted to the red, and the theory is that the further they are, the more they're shifted, and that's what they call Hubble's law. Edwin Hubble first suggested that the reason they're red shifted is because of the Doppler effect of expansion, and that seemed to explain for most of them. And so they call that Hubble's law, and that's why the Hubble telescope is named after Edwin Hubble and all that. Well, William Tift was collecting data on red shifts, as they're called, that are not red. They're going the other way. There are a few. They're called aberrant red shifts. And they seem to they raise doubts about the possibility that the universe may be expanding, because if it's expanding, some of them are coming at us rather than going away from us. And so some of these clusters of galaxies and so forth, he also discovered are all a multiple of a discrete value. All the red shifts are not, it's not like a violin where you can get any tone you want. It's like a piano. You can only get the key that you hit. You follow me? There's discrete steps. Well, he's discovered that there's discrete steps in the red shift, which implies that it's not a Doppler effect. It's something else that's causing that. It's digital is the point. Whoa, wow. So if they're discrete quantum levels, it turns out that they may correspond to discrete atomic levels, and they may all derive from the speed of light changing. And Satterfield was the first to recognize that. If Satterfield proves correct, then this could explain the quantization of the red shifts. That's still yet to be confirmed. Specific values of c, or the velocity of light, govern the quantization of emitted wavelengths, and that would result, and since this was originally put together, Satterfield has confirmed that mathematically. So there is a stretch factor having to do with the space that we're in. And we understand that that stretch factor is in the region of about 10 to the 12th, 10 with 12 zeros after it. And we're indebted, and that has to do with the quark confinement. I don't want to get into all that here. But the point is, Dr. Gerald Schroeder, the nuclear physicist, resides in Jerusalem, a good friend. Now, he's a Jew. He's not a Christian, but he has written a great book called Genesis of the Big Bang. He points out that the stretch factor is about the expansion of the universe. It's in the neighborhood of 10 to the 12th. And that comes from nucleosynthesis and some quantum physics information. And he takes the exponential expansion of that, and he relates it to the chapter 1 of Genesis, where day 1 is 8 billion years, second day is 4 billion years, then 2. Anyway, the net of it is the 16 billion years times 365 days a year, if you're going to use that number, approximates 6 with a lot of zeros after it. And what's interesting about that, if you shrink that by the expansion factor, you come down to 6 days. So was the universe built in 6 days? Could be. Do they now appear to be 10 to the 12th? Could be. So he sees that as strictly a stretch factor, the same stretch factor of the expansion of the universe being correlative to the difference, apparent difference in our minds, to the 6 days of creation, in which only God's clock was running. Adam just shows up in the last day, right? So who knows? That's just one way. I don't necessarily side with this particularly, but it's just another way to show that it's another way to explain the apparent discrepancy to most of us. But I'm more intrigued with what Paul has to say than what Jerry Schroeder has to say. In Paul's letter to the Ephesians, in chapter 3, Paul makes an interesting remark. He says that Christ may dwell in your hearts by faith, that ye, being rooted and grounded in love, may be able to comprehend with all saints what is the breadth and length and depth and height, and to know the love of Christ which passes knowledge, that ye might be filled with all the fullness of God. So it's a devotional tapestry here, except on the way he makes a strange remark. He says, what is the breadth, the length, the depth, and the height? Did you notice that? How many dimensions are there? 4. My goodness, is Paul consistent with contemporary physics? Do you think he realized the universe has 4 dimensions? I don't think so. But the Holy Spirit that was guiding it certainly knew all about it. So Paul's expression here, I believe, vastly transcends his own understanding. if you take these terms in the Greek, platos means the breadth, suggesting great extent. Length refers to length as we think of it. Depth, bathos, the deep things, like the deep things of God, whatever. And height, of course, is height of place, hupsos. But the point is, these are all 4 dimensions that are descriptive of the spaces we know it today. The Epistle to the Ephesians is surprisingly sophisticated from a physics point of view. That leads us into this discussion of hyperdimensions. That's just a fancy word for spaces that have more than 3. You and I are used to 3 dimensions, right? But if you can talk about spaces of more than 3, but then you're dealing in what's called hyperdimensions, okay? We've just gone beyond Euclid. When we were in school, all of us had what's called Euclidean geometry, which is the geometry limited to 3 dimensions, naturally. We had enough trouble with that. We didn't need more, right? But in 1854, one of the most important presentations of mathematics was given on June 10th by George Riemann, where he introduced the concept of metric tensors. I won't get into exactly what they are. It's an advanced form of mathematics. It deals with hyperspaces. It took 60 years before it was found practical application, and it got application by Einstein in his theory of relativity. That was the mathematics that made his theory testable. And by the way, Einstein went to his death frustrated. He got his breakthrough because he moved up 1 dimension from 3 to 4, and suddenly the theory of relativity unfolded. But he went to his death frustrated because there were certain things that he couldn't reconcile that after his death were reconciled by successors doing exactly what he did, going up another dimension. Kaluza and Klein, in 1953, were able to reconcile light and supergravity into an integrated presentation. And it was in 1963 that Yang and Mills fields were developed. Now they've unified all the 4 major force fields into a common rendering, electromagnetic and both the nuclear, weak and strong nuclear forces. Anyway, so in today's world, they now, since 84 on, you have all kinds of theories which has to do with what they call superstrings, and they vibrating in 10 dimensions. The common understanding among people who deal with these things is that we live in at least 10 dimensions. And it fascinates me that in the Bible, the only number of strings it mentions is 10, by the way, as an aside. But perhaps far more interesting than that, there was an ancient Hebrew writer by the name of Nachmanides, wrote in the 13th century. And he concluded by studying the Torah, the book of Genesis, he concluded that the universe has 10 dimensions, but only 4 are knowable. And he concluded this in his commentary on Genesis that was published in 1263. Why am I mentioning that? Well, particle physicists today, I should say the 20th century, have concluded that we experience 10 dimensions. 4 of them are directly measurable, 3 spatial dimensions at a time. We can measure those. 6 of them are curled in less than 10 to the minus 33 centimeters and thus are inferable only by indirect means. They're clearly there. They can prove it mathematically. They can't get at it. So 4 are knowable, 6 are not. So our physicists have spent millions of dollars on atomic accelerators to discover what Nachmanides concluded from studying his text of Genesis. So there are only 2 kinds of people that can really deal with hyperspaces, spaces of more than 3. That's mathematicians with special training. And relax, I'm not going to try to go that way. Okay, here. The other people I can deal with them are small children. Small children have no problem. They can deal with that. Now, Edwin Abbott was a churchman in the turn of the century. He wrote a novel called Flatland. And his little novel is a useful technique to get... We can't move up. If I tried to talk 4 or 5 dimensions to you, we'd quickly be not communicating. But Edwin Abbott played around the other way by imagining a universe of 2 dimensions. And we can learn from some of the things he did. I want to introduce 2 people to you. And I'm going to ask you to be, compassionate, because these 2 people have a very serious handicap. They live in only 2 dimensions. Mr. and Mrs. Flapp. And I'm drawing on Abbott's concepts here. And their universe is 2-dimensional. And if they each live in their own universe, two-dimensional universe, they have no conception of the other. They have no way to make the transition. But if I come along as a three-dimensional person, I can easily move that one into their universe. For what to them is a miracle, to me is casual, right? So we learned something there. There's something, we can go further than that. I also have another capability. I can incur a proximity to each of them that is more intimate than they can have with each other. I could put my finger 1/1,000,000th of an inch away from each of them, no matter where they are. See, I can enjoy a form of communion with both of them that they can't even have with each other, because I have the advantage of an additional dimension. See where I'm headed? We can draw some understanding of hyperdimensionality from this little exhibit here. If I stick my finger through their universe, what do they see? They don't see a hand. They see a dot that becomes a circle and then goes, they see the two-dimensional subset of what I am, okay? If a ball falls through their two-dimensional universe, they see a dot that becomes a circle, it becomes a dot and disappears. They never see the ball. They see the two-dimensional representation of the interference of that ball with their universe. Okay. Now, how would you communicate a three-dimensional object to a two-dimensional universe? Suppose I want to communicate to Mr. and Mrs. Flat about what a cube is, a box that has four sides, a top and a bottom. How would I do that? Well, one way I could do is by a two-dimensional projection. I could try to project that box into two dimensions. But that isn't very useful. They wouldn't be able to grasp that too well. If I take a four-dimensional cube, and there are such things, and project them in 3 dimensions, you can do this on the internet, you quickly discover they're not at all intuitive as you start playing with it. Now, this is a 3-dimensional projection of a 4-dimensional hypercube, but I couldn't do the simulation for you here. Not very useful in any case. Another way I might do this would be to unravel the cube to the 2 dimensions. I can take the box and unfold it. I can unravel it. That'd be one way I could try to communicate a 3-dimensional object into a 2-dimensional universe, right? Not still a bit awkward, isn't it? Well, there is a 4-dimensional cube that can be unraveled, and it's called a tesseract, or a Hinton cube. And the only place I've ever seen this actually used may surprise you. The only place I'm aware of this, other than in geometry class, the only place I've ever seen this used is in a painting by Salvador Dali. His representation of Corpus Christi is, in effect, a tesseract. It's a 4-dimensional cube unraveled in 3 dimensions. And it stunned me to realize that Salvador Dali had that kind of mathematical insight to understand what he was doing here. Phenomenal. Phenomenal. Hyperspaces. We've talked about n-dimensional spaces. We've given you a 2-dimensional example from Mr. and Mrs. Flat from Edwin Abbott's book called Flatland. And the Hilbert space is also, there is a space that has an infinite number of dimensions that mathematicians attempt to deal with. But let's talk about we talked about time travel. Let's talk about hyperdimensional travel. Is it possible, if I have a 6-sided space, here's a 6-sided space, 4 walls, a top and a bottom, right? Is it possible to enter and leave that space without going through any of the 6 sides? It happened. The disciples were in an upper room, frightened, nervous, confused, doors locked, windows shut, nervous, and Jesus shows up right in the middle of them. They're shook up, understandably. They think he's some kind of ghost or a spirit. Hey, guys, handle me and see. A spirit does not have flesh and bone as you see me have. Have you got anything to eat? My kind of guy. No, Jesus has the ability to enter and leave a 6-sided space without penetrating any of the 6 sides. And yet he's physical, but he's not limited to 4 dimensions. Mathematicians will argue that he has to have at least 10 to do that by some transforms. Well, maybe. But there's a very interesting, whatever he has, we will have. One of my favorite passages is in 1 John chapter 3, verse 2. And unless you have a physics background, you probably don't understand what John is saying here. John says, "Beloved, now are we the sons of God, and it hath not yet appeared what we shall be, but we know that when he shall appear, we shall be like him, for we shall see him as he is." See, I can show you a two-dimensional representation of a three-dimensional person. That's called a photograph. A two-dimensional representation of a three-dimensional person. What John's saying, we know that when he shall appear, we shall be like him, for we shall see him as he is. We're not going to see a 9-dimensional representation of a 10-dimensional being. Whatever it is that he has, we know that when he shall appear, we shall be like him, because we shall see him as he is. I think that's a statement that goes far beyond the physics of the average reader in terms of what really is, what the Holy Spirit is communicating to us there. Staggering. Gravity and space-time. The influence of gravitational force on the curvature of space-time. Space tells matter how to move, and matter tells space how to curve. They're intimately connected. Do you realize, by the way, that what we know about the physical universe is limited to a 5% sample? Do you know that they now understand that 95% of matter is invisible? They're hunting for it. There are all kinds of theories. They know it's there mathematically. They can't see it. That's why they call it dark matter. And there's all kinds of astrophysical experiments to try to get a handle on where is it. Because it's we only understand 5% of the total. If you took a course in physics and got 5 questions right on a question of 100, what kind of grade would you get? See, that should lead to, if nothing else, to some humility. The early scientists, Sir Isaac Newton and others, went at their task in an attitude of humility before God. Their search was for truth. We live in a culture in which it denies the existence of truth, and it rejects any explanation that isn't repeatable in the laboratory. We blinded ourselves to really understanding. But anyway, boundaries of reality. Now, we've gone on the big side and explored a few things in largeness, right? The next time we get together, we're going to go the other way. We're going to talk a little bit about smallness. We're going to get a little bit into quantum physics and subatomic particles. We're going to deal with smallness. And we're going to discover something even more shocking than the fact that the universe is finite on the big side. We're going to discover that the universe is finite in smallness, and that will shatter our understanding of common things. Let me give you an example. If I have a line, piece of string or whatever, I can cut it in half, right? Sure enough, whatever it is. And I can take whatever I have left over, and I can cut it in half, right? And you would think that I could do that forever. Maybe not physically, but in my imagination, whatever I've got left over, I can always cut in half, right? Wrong. Turns out not to be true. There is a length. If I get down to that length and I cut it in half, it suddenly doesn't disappear. It's everywhere at once. It loses a property that physicists call locality. And it's 10 to the minus 33 centimeters. It's very, very tiny, but there's no length smaller than that. Anything that has length is a multiple of that. It's an indivisible unit. They call that a quanta. That's why the study of this is called quantum physics. Okay? They lose locality. There's a minimum length called 10 to the minus 3 centimeters. There's also a minimum length of time, 10 to the minus 43 seconds. Time can't be divided any smaller. That's the smallest unit of time you can imagine. It happens to be the length of time that the speed of light takes to go through your iris. That's called a twinkle of an eye. Not a blink of an eye, twinkle of an eye. Ooh, what could that possibly have? I think there's a hyperdimensional transform that we call the rapture that's going to take place. So we'll go in talking about linear assumptions in a nonlinear world when we get to it next time. And with that, let's stand for a closing word of prayer. Father, we thank you for who you are. We thank you that you care so much for us, that you chose to actually enter our environment, to become a person like us, and yet with perfection and with an ability to demonstrate an eligibility for something that we could never make. That you gave yourself on our behalf to pay our debts. We stagger as we begin to discover how far you've gone on our behalf. We thank you, Father, for the insights that you've given us in your word. We continue to stagger as we discover that as advanced as we think we become scientifically, your word has gone way ahead of us all along. We thank you, Father, that you cared that much for us to communicate with us and to go to such extremes on our behalf. We do pray, Father, that through your Holy Spirit and through your word, you would help each of us grow in grace and the knowledge of our coming King. We pray, Father, that through your word and through your Spirit, you would help us understand what it is that you would have of us in the days that remain, as we commit ourselves without any reservations whatsoever into your hands. In the name of Yeshua, our coming King, our Savior indeed. Amen.